Anybody know what penultimate means?
Finality?
The one, second to last.
Second to last.
Second to last.
Say the word again.
Penultimate.
Keyword penalty. If you're not first, you're last.
Penultimate. I learned it in grad school. I even remember which class it was. It was in a state estimation class. It was like a random number generator algorithm, like a manual one, where like you turned to like the penultimate page in the chapter and you took the number from it and you mashed it up with some other thing, and then that was like supposed to be a random number. And yeah, it was interesting. I had to look up what penultimate meant, and ever since then, I have remembered it. And then like it's funny because like you don't really need to use it, but it's fun to use. Like penultimate is way cooler sounding than second to last. So I don't know. I like it anyways.
Is there a band name in there?
Probably penultimate. Yes. I feel like there is, but I also feel like me coming up with it on the fly, there's danger in that word I should stay away from. So, equilibrium and stability properties of LTI systems. 5.2. So, we talked last time about some LTI system properties, including the main, big one, superposition, right? And then we're also going to talk today about stability. Oh, and the other one was differentiation and integration of inputs. We talked about last time. And this time we're going to also talk about equilibrium, which is another sort of property of an LTI system or of any system. And then finally, stability as well, which is another property. And these properties are really useful to sort of classify systems, so and to solve for things with them. So linear systems and their property of superposition is really useful for analyzing them. And then equilibrium and stability are two really useful concepts as well. So for a system, and then on Monday, I'm essentially just going to do examples. This is actually the ultimate lecture. And then I'll just do examples. So for a system with LTI, state space model, our usual standard form, x dot equals ax plus bu, y equals cx plus du. The model is in equilibrium, state x naught, if all time derivatives of the state vector are zero, or the zero vector. So if they're not changing, right? Not changing. So this implies that ax naught plus bu equals zero vector. So this equation is equal to 0 instead of x dot. For constant input u bar, this implies ax naught equals negative b u bar. And u is a vector, but I'm going to just put the bar and not vector and bar because it just seems confusing. So this is what's implied by the fact that we're in equilibrium. If A is invertible, as is often the case, there is a unique solution for a single equilibrium state. So x naught is equal to negative A inverse B U bar. So A being invertible is the condition for having this solution, right? And if it is invertible, then there's only one equilibrium state. However, there are systems for which A is not invertible, okay? And when that arises, instead of just throwing up our hands and saying, well, I don't know, maybe there's some equilibrium states in there, whatever, we can actually find them, but it's a longer process. I'm not going to go through that. But suffice it to say that instead of there being simply a single state, there is a subspace of the state space that becomes equilibrium. So, say in the simple case where we've got two states, it's like x1 and I guess x1 would probably do this. We wouldn't do that to us. x2. In that simple case, typically x naught is our only equilibrium state. But so this is the state space, right? This is the plane. If there are only two state variables, the plane is our state space, right? So there are situations though where you can have like a line, which is a subspace of the plane, right? This could be the equilibrium subspace if A is not invertible. That's just sort of an example, but there could be some subspace. So there could be some larger space, and I know you guys haven't all taken linear algebra yet, so you will be next semester. There's like the math department's like, hey, so we have like a lot of students taking linear algebra. There's like a waiting list for the linear algebra. I heard they're gonna open up another section or something. Get you guys all in.
I hope it's not.
So I don't know. I don't know what the word is yet, but
I said I hope it's not a
yeah.
I will go on the record saying that. Okay.
The other section, we got 9.
Oh, is it 9? The other section? Oh, okay, cool. Yeah, yeah. So because hopefully, because you guys need to be in it for system dynamics. So yeah, but there's going to be a lot more of this, like the discussion of like the state space and whatnot, how to interpret things. And this is all sort of linear algebra stuff. I don't expect you guys to be like super tuned up on it yet. But suffice it to say that we can all understand the idea that there's a plane and there's a line in the plane that can be like part of the plane, but not the whole plane, right? So that's called a subspace. And that could be an equilibrium line. So for instance, you could have an initial condition that starts somewhere on this line, and if you had no input and initial condition that started on this equilibrium line subspace, nothing would happen if you let it go. Like if you just like stuck it there, so you had your x1 initial be whatever this is, and then your x2 initial be whatever this is. The initial condition being in that subspace, that equilibrium subspace, says, oh, you're in an equilibrium spot, nothing changes. Now, if you moved off that equilibrium spot and let it go, it probably would change. Well, it definitely would change if it's not an equilibrium point too. So there's some subspace that can be in equilibrium as well. That's not something that we're going to discuss in depth this term. We might discuss it more next term. But for now, we're mostly thinking about this case where A is invertible and the equilibrium is just the one point, just the origin. So when all the state variables are equal to 0, that's the equilibrium. Okay. So if x is perturbed from an equilibrium state, x naught, the response, so which is to say the solution to the state equation, which we've learned how to do in MATLAB, right? Just like simulating it, right? A step response or whatever. We learned how to do that, but we haven't really learned how to solve it analytically yet. But if we were to solve for what that response was, it can asymptotically return to equilibrium. So if you moved it away from equilibrium, it can go back to equilibrium. That would be this case. And we call this asymptotically stable. So it doesn't have to actually arrive at the equilibrium value in finite time, but it has to, in the limit, it should, as time goes to infinity, it should approach the equilibrium point. Another possibility is that it diverges. So this we call just unstable, I guess. Unstable. So something that diverges, so say you perturb it a little bit, and instead of going back to the equilibrium, it goes off to some infinite value, diverges. That would be an unstable system. So there's some subtlety to this, but if you think of only the upper half plane of an inverted pendulum, you know this. So everybody try to balance a broom on their hand? Try to do that? It's pretty fun, right? That's called an inverted pendulum. So you're moving around your hand to try to balance it, right? But if you don't actively try to do something with your hand and stabilize it, it's gonna fall over, right? So in equilibrium, if this thing's just perfectly straight up, and you were like perfectly still, and the air wasn't moving, that's an equilibrium point, right? As long as nothing disturbs it, it's not gonna move, it'll just stay vertical. But if it gets perturbed at all, like a little wind gust goes by, or you kind of move a little bit, you sway a little bit, that thing's going to start to fall, right? And unless you actively try to balance it, it's going to fall. So that's an unstable system. That's an unstable equilibrium point, is that vertical point. So we're going to ignore this pendulum this way for now. So just this pendulum, that's unstable. This pendulum's actually stable, right? If you perturb it a little bit, it's going to come back to equilibrium. So that's the quintessential unstable system would be an inverted pendulum. Okay. Another possibility is that instead of so it doesn't go back to equilibrium, it doesn't go off to infinity. Instead, it just stays put, or it just sort of oscillates, going round and round and round. Okay, those are the three possibilities. So if it does that, it's kind of in between, right? It's not going back to equilibrium. It's not going off to infinity, but it's just hanging out, right? And we call that marginally stable. That's a really big Y. Marginally stable. So what I was drawing up here, which is sort of like we're just sketching around, is actually called a phase portrait. So it's a parametric plot of state variable trajectories with time implicit. So it's the values of the state variables plotted versus each other. And time it's a parametric plot because time isn't explicitly in here, right? You guys drew parametric plots, I don't know, high school, college, or whatever. I think it's pre-calculus is the class that you do that in. You draw those cardioid graphs. You guys remember those? Oh man, cardioids are the best, right? They look like this. They're like, oh yeah, but that was horrible. But yeah. Oh, that's better, but not great. Usually they're symmetric. So, yeah, cardioids. It's because it looks kind of like a heart, right? And like, you drew one that looked especially like a heart, and then like showed it to that special someone in your class, and that special someone blushed.
Or laugh.
Yeah.
Or laughed. It's true. This could be a painful memory for some. Okay, so these are useful ways to visualize how a state evolves. So the trajectory of the state in state space. It's really useful, especially when you think about equilibrium points like this. So phase portraits are exceptionally useful for understanding nonlinear systems. But they also give us a nice way to understand stability. So we're going to look at figure 5.1 in a second, but I'm going to talk about this mention of nonlinear systems and phase portraits. So we're learning currently a lot of really interesting methods for dealing with linear systems. And there are a lot of ways to characterize linear systems and understand how the system will respond, its sort of properties at a high level. For nonlinear systems, a lot of those definitions don't really apply. So you kind of, like, you get a nonlinear system, you can simulate it, so you can use MATLAB, for instance, to simulate it, but that doesn't really tell you anything globally true about it, right? Like, so you could simulate for some initial condition and some input what happens, but that doesn't tell you, for instance, is this stable or not? Like, you just, for one case you know what happens, but you don't know in general. Like, what if I picked another point? Like, would it be stable? Like, would it go off to infinity? Like, would my system blow up? Like, you don't know if you have a nonlinear system, oftentimes, from just looking at the equation, what's going to happen. And looking at one simulation doesn't really answer that. So you could do a bunch of simulations. There are a lot of ways to explore it, but one way to explore it is to look at its phase space, its phase portrait. And I hope next semester I'll get a chance to discuss it in more detail, where we'll talk about how to draw a phase portrait for nonlinear systems and understand aspects like stability from that. So it's really, really cool stuff. So for now we're just kind of like saying, oh, phase portraits, cool. Like, we're going to use them for this, but then we're not gonna spend a ton of time dealing with them. But hopefully we'll return. There's just so much I want to teach you guys about this stuff. But next semester I'll be able to teach you a lot more than I can now. So this is figure 5.1. So these are the phase plots for 3 different cases. So x1 and x2. So once again, a second order system. So just 2 state variables. We plot them versus each other, and time is implicit. So we start out some initial condition, and if it's asymptotically stable, it's going to approach the equilibrium value. So equilibrium is x naught, the origin, and if you start it off, you perturb the state from equilibrium, and you just let it go, it's going to go back to equilibrium. Okay? Yeah?
Would that be similar to a situation with like a damper and returning to like, I don't know, like a steady state or something like that? Or?
Yes. So the steady state value is an equilibrium point. So if you have, for instance, a step input, so when you guys were doing your motor lab, you guys put in a voltage. It was 10 volts or whatever you put in. 10 volts, and then you watched the thing speed up to 10 volts, or to whatever its max speed was, and then it came back. So what you were doing is, so when no voltage is applied, what you have is this situation, but U bar is 0. So your x naught, your equilibrium point, is 0. So that's why it goes back to 0. But when you apply that voltage, the equilibrium point moves, right? So then it becomes whatever this is. You have to compute it. It becomes that, and so it decays to that new equilibrium point. So this equilibrium point, it's x0 if you have no input. If you do have a non-zero input that's steady, it moves. So it might be over here, but it'll still come back to that point. So wherever the equilibrium is, if you have an invertible A, which that system does have an invertible A matrix, you have one point, and you can move it around based on what your input is, your steady input is. Yeah. So, cool. And actually, oh God, like now that I think about that, that would be such a perfect system to draw this for, because that system is second order. So it's state, we would have, like, for instance, this would be omega j, and this would be IL, current. And so you would say, when you put in a voltage, non-zero voltage, you're actually moving this equilibrium around on this axis. That's what you're doing. So IL. So you can be over here, you can be over here, you can be over here, depending on the voltage that you put in. But the current's always going to be 0 or roughly 0. There's a little bit of damping that it's got to apply a little bit of torque to, but it looks like 0 because it's such a tiny amount of current it has to supply to overcome the damping, damping. So yeah, so it's really, it would be a cool system. We should draw these phase portraits. I should ask for that in the lab next year. The lab right now. Draw a phase portrait of your, oh man, so cool. Okay. Yeah. This is what happens. This is how it grows every year. No, I compress it like a JPEG or an MP3. That was this class I talked about that, right? I thought so. Okay. Cool. So, excellent. So this is generally state space thinking for stability. Okay. The same stuff applies if you have input-output differential equations. Say your output can't be changing. So instead of just having, a bunch of states that have to have time derivatives equal to 0, you have your independent or your dependent variable y has to be, the time derivatives of it have to be equal to 0, right? So you can think of it in those terms as well. But what we're going to do now is we're gonna say, okay, this is generally true. This is generally like some decent definitions for stability. But let's define stability in terms of the free response, which for LTI systems is a really nice way to actually find tests. So these definitions are great, but notice that it doesn't really give you a great way to test it. Like, you'd have to, in theory, test every single starting state and make sure that it's going to come back to equilibrium. And that's obviously not a good plan. So we want to come up with a better way to test it. So if we define in terms of the free response, that's like a step along the way. So using the concept of free response, which is no inputs, just initial conditions, and then letting it evolve, right? We define the following types of stability for LTI systems. And this is a reference, I didn't check this one, but anyways, it's Nice. It's something you're going to be typing into Amazon or BitTorrent soon. It's the textbook for the system dynamics class. It's one of the textbooks. So we're going to still use Rowell and Wormley, but we're also going to use this Nice textbook, which is controls textbook. Because we're going to do not just system dynamics, we're going to also do some controls. That's the other part of that class name. So much fun stuff to teach you. Okay, so awesome. And so the first definition, we're going to just essentially restate this asymptotic stability definition in terms of free response. So an LTI system is asymptotically stable if the free response approaches an equilibrium state as time approaches infinity. So free response is something that we actually can analytically solve for. And so we're not relying on like a bunch of simulations anymore. We can analytically determine the free response and make some draw some conclusions. Similar with unstable. Unstable is now defined as a free response that grows without bound as time approaches infinity. So decaying or increasing, growing. And then marginal stability is defined as a system for which a free response neither decays nor grows but remains constant or oscillates as time approaches infinity. Okay, so these statements imply that the free response alone governs stability for an LTI system. Recall that the free response, y free of a system with characteristic equation roots lambda I, multiplicity mi for constant ci. So before I write it, let's recall what these things mean. So remember when we're solving a differential equation, we have to find the homogeneous solution first, right? The way we find the homogeneous solution is to write the characteristic equation, which is a polynomial in lambda typically, right? So if it's a second order system, it might be like lambda squared plus 49 lambda. I just feel like 49 plus 2 equals 0. So we would solve for lambda 1, lambda 2. There would be two solutions. And that's going to help us construct our homogeneous solution, right? But if there is a repeated root, so maybe you had like 3 roots, so there's an omega cubed or a lambda cubed characteristic equation, third order. Maybe you have your lambda 1, 2, 3 are, say, 4, 3, 3. Well, these two are equal. So we say that lambda equals 3 has multiplicity 2. Okay? If there's only one of them, which is the normal case, then lambda is just the multiplicity 1. So that, like, 4 has multiplicity 1, 3 has multiplicity 2 in this case. So I say that because we can write the free response as being the sum over all of the i's. So I could write to n, which is the order of the system, but I kind of got lazy on this, I guess. I just don't want to muddy the water. Ci is a constant that's found from the initial condition being applied. So Ci, and then instead of just being e to the lambda it, which is the case when we have no repeated roots, I'm going to put in this t term. Because remember, if you have multiplicity greater than 1 for any of the roots, you have to include in your homogeneous solution another factor, right? T raised to whatever the multiplicity is, minus 1. So if multiplicity is 1, which is the normal case, this comes out to be t to the 0, which is just 1, right? So this doesn't affect most of the terms, but it does affect an occasional term. Then multiply by e to the lambda it. So that is the free response, assuming that you've solved. So that's the homogeneous solution, but once you apply the initial conditions to it, and you've solved for Ci, so C1, C2, etc., then you have the free response. Okay? So each term will either decay to 0, remain constant, or increase without bound, depending on the sign of the real part of the corresponding root of the characteristic equation. So the real part of lambda I. So what did that mouthful mean? So if you look at lambda I, if lambda I is real, let's just think about it as being real for a moment. If it's real and it's positive, the term associated with it is going to exponentially increase, right? So if any of these is real and positive, it's going to be an unstable system, right? Because it's going to increase without bound. If lambda I is negative, is a real root, and it's negative, that's going to exponentially decrease to 0, right? So that's going to go to equilibrium. So that's stable. If lambda I is real and it's 0, then it's e to the 0, and it's just a constant term that's left. And that would be marginally stable. That contribution would be a marginal stability contribution. So the real ones are relatively easy to figure out. Well, let's think for a moment about what happens if lambda is complex. So let's say that your kth lambda was a complex lambda, and it was some real part plus j omega plus some imaginary part. Then we would have an e to the sigma plus j omega t term, right? That would arise from that. So e to the lambda k t would just be e to the sigma plus j omega t. Well, you guys remember the property of exponentials that allows you to rewrite this as e to the sigma times e to the j omega t, right? Because when you multiply two exponentials, you just add their exponents, so you can also split them up by doing that in reverse.
Wouldn't it be sigma t?
Yes, sir, it would be sigma t. Excellent. Good catch. Let's say I was testing you. So, do we recognize this? This looks familiar, doesn't it? My friend has this tattooed to her palm. This is found from Euler's formula to just be a sinusoid, right? Sinusoid. This is just a real exponential, right? So it just like the other exponentials we were talking about, it can either grow, stay at just 1, or decay to 0. So those are the possibilities. So what results from a complex root then is either a sinusoid with increasing amplitude with an exponential increase, if sigma is positive, a constant amplitude that doesn't change if sigma is 0, or a decaying amplitude sinusoid that decays with a negative exponential envelope. So if sigma is negative. So it's actually the real part of each root of your characteristic equation that dominates stability. So it's the stability is all determined by the real part. And that's what I mean when I say, so it can do any of these things depending on the sign of the real part of the corresponding root of the characteristic equation. In other words, for an LTI system, the following statements hold. 1, an LTI system is asymptotically stable if, for all lambda I, so for all the roots of the characteristic equation, the real part is negative. Okay? So that's our condition for stability. Second statement we can make is that an LTI system is unstable if, and then this is a typo, if for any, instead of all. So this is a key typo, so please fix that in your notes. So an LTI system is unstable if for any lambda I, the real part is positive, which is to say, one fly in the soup sort of ruins the whole batch, right? Like if you have one of these lambdas that go off to infinity, your whole system's unstable. So stability requires all of them have negative real parts. Instability, you only need to have one that's not, and then you're unstable. And then for marginal stability, it's marginally stable if for all of the roots, the real part is less than or equal to 0, and at least one of them is equal to 0. So if all of them were less than 0, then we would just be stable, right? But marginally stable occurs if one of them is 0 or more than one is 0. At least one of them has to be 0. And then the rest are stable, are negative real parts. So that's that one. And then I'm just gonna, if there are no questions on this, I'm gonna discuss forced response stability for just a moment. Any questions? Okay. So an alternate formulation of stability definitions above is called bounded input, bounded output, or BIBO. The definition of stability states the following. So this is from Nice again. This reference didn't come through. So a system is Bibo stable if every bounded input yields a bounded output. So that's slightly different than the other definition, right? It's talking about inputs. Previously, we had all our inputs set to 0. This has a lot of times, a lot of systems that are stable in the free response sense are also Bibo stable, but not every single case is like that. There are some exceptions. Similarly, every a system that's Bibo stable is usually stable in the free response sense, but not always. So this is a sort of an alternative formulation. We mostly focus on the free response definitions, but it's good to know that this one is out there too. So a system is Bibo unstable if any bounded input yields an unbounded output. So let's look at what that looks like. So you have an input. What is a bounded input? So it's an input that you can draw bounds around. So as long as you can find some bounds that your input never goes outside of, I mean, they could be huge bounds, but as long as they're bounded somewhere, then your input is bounded. If you put that into the system and you get out, so output, if you get out an output that's bounded, they don't have to be the same bounds. They can be other bounds. But if you can draw some bounds on an output, I can't really go backwards. Some bounds on the output as well, then it's stable, Bibo stable. But if you can't, if it increases without bound, if you can't draw a bound around it, that would be Bibo unstable. So marginal stability in terms of Bibo means that a system has a bounded response to some inputs and an unbounded response to others. Okay. So one example of that is a second order undamped system response for a sinusoidal input at the natural frequency. Okay. Whereas every other input for that system has a bounded output. So the last thing I'll do is I'll draw a little system that is like that. So a second order system that has no damping, just a spring and a mass. This system, if you apply a force to it, sinusoidal force, and we say we put it in at sine of omega t. If you put it in at virtually every possible frequency, so this is bounded, right? This is a bounded input, just a sinusoid. At most frequencies, the output is bounded for this system. But if you happen, so it's bounded, so it's marginally stable in the sense of the free response system as well, right? You let it go, it never damps out, it just oscillates. And if you put in a sine forcing in this system for any frequency other than the one no frequency, then it's fine, it's bounded too. So it's Bibo stable for most of the inputs. But if you set omega equal to omega n, which is the natural frequency of this system, and as you'll learn more about next term, is just equal to the square root of k over m, then the output is actually unbounded. It grows, so it's sinusoidal, but it's sinusoidally growing without bound. And so that system would be marginally Bibo stable, because for some inputs, it's perfectly stable. For other inputs, it's not. Okay, I gotta give you guys these. Can somebody volunteer to return them to Mrs.